Thank you. Yeah, welcome to my course on matrix equations and model reduction. Actually, it should be called model reduction and matrix equations because we do first a lot of model reduction before we come to the matrix equations. Maybe I just should introduce for the exercise sessions I brought two postdocs, Tobias Breiten and Li Hongfeng. Can you get up just for, or probably you have met them. They will be in charge of the exercises in the afternoon, but I will be around as well. Okay, so I heard you had already nice lectures last week on topics related to matrix functions, basically. And I assume you learned a lot of things there that will be of use for this course as well. In particular, Krylov subspaces are important for part of my lecture. So I assume certain familiarity with Krylov subspace methods, with the Arnoldi method, to some extent with rational Krylov subspaces, as Marlies had it in her lecture. But we will use them in sort of a simpler way or in a simplified fashion. So if you see that I assume something that you don't know, just raise your hand and ask. There's another issue related to the topic of model reduction that comes often a little bit as an obstacle for students to get acquainted with the subject. Namely, it builds upon many things. It builds upon linear algebra and matrix theory. It builds upon numerical linear algebra. That's why it's part of this course. But it builds also on other things like approximation theory and complex analysis, function theory. It's not going very deep into the subjects, in particular not in the range of this course. But again, if you're not familiar with the concept, just raise your hands and ask a question. May I just ask who took a course on complex analysis or function theory? Or let's put it the other way, who didn't take a course on that subject? Okay, only few people. So we'll see how that goes. I think we're not using too much of it, so should be easy to follow. So the outline of the whole. So you have obtained this nice book with a subset of my slides. And you also have obtained, because I have to admit that for one part of the introductory lectures, I wasn't able to prepare slides, and I think it's better to do it on the blackboard in a way. You also have obtained at the end of this book, there is something called mathematical basics. That's basically what we are doing today, and at least in the second half of this morning's lecture. I will introduce you to some concepts that are basic to the understanding of what we are doing in the other coming lectures. In particular, some concepts from systems and control theory. Unfortunately, I first sent the wrong file, so there are a few typos in that part, but we'll come to that later. Okay, so I will give you an introduction with some motivation and some motivating examples, what you can do with model reduction in real life. Then we have to go through this technical part where I have to lay the foundation so that you all are on the same level to understand the rest. And then there are certain ways to do model reduction, and we will focus on doing projection-based. You probably all know what a projector is from linear algebra. All the methods that we will use make use of the concept of projection. So I will get into that a little bit. And then we have two big classes of model reduction. One are based on interpolation conditions, and we will work out the connection between interpolation and projection that is important here in this area already in this part. And then the other big class of methods is balanced truncation. And in balanced truncation, we will see that we have to solve matrix equations. So that brings us to the first part of the title of this course, how to solve these matrix equations that are the bottleneck computation in balanced truncation. And you will see that in MATLAB, on your notebooks, you will be able to solve systems of nonlinear equations with a few billions of unknowns with the methods that are around in this field. You don't need a supercomputer to do that. Although I don't think we will get to implementing such a method at the end. But yeah, that's the course outline. So in the introduction, I will give you a brief overview on the basic concept or the basic task in model reduction for dynamical systems, and talk about some application areas that were historically driving the field. Nowadays, model reduction is, I would say, a major tool in all of computational science and engineering. It doesn't solve all the problems you have with high-dimensional data and high-dimensional problems, but in many cases it can be a very helpful tool to make some simulations or some optimization, some design possible at all. Yeah, okay. So first, I should say that at the beginning we'll have everything on these slides, but later on you also will have to take notes at some points. It's not everything is in the slides, and not everything is in this handout that I gave to you. But for the beginning, I just used the slides. So usually we have a physical problem, a dynamical problem, instationary problem. You can talk about model reduction for stationary problems related to elliptic partial differential equations as well, but we will not do that here in the course. And our physical problem is described by states. So these are, say, the temperature. If you have a three-dimensional object and you're interested in the temperature, like this notebook, you put it on your lap and you feel that it's getting warm. So you may want to, if you're a designer of a notebook, you may want to know what's the temperature that is produced while you work on your notebook so that you can still have it on your lap. So the temperature in all the points that make this notebook, usually not the continuum, but a discrete version of it. You use a finite element grid to discretize it, and you have the nodes in your grid, and you're interested in the temperature in these nodes. That's just one example of many. So these are the states, or collection of all the temperatures in these nodes of your finite element net. And depending on the granularity of your net, you have a lower or higher number n. So in some applications, you need model reduction already if n is 30. I will explain that in a minute, in which application areas that's the case. In some situations, you're fine with a system with 100,000 states because you have an efficient solver for linear systems. But sometimes you want to bring it down, so that depends on the application. So one thing that you may encounter is when you do a model of a physical problem is that you have redundancies, or you describe your model with too much information for the quantities of interest that you have. So you may, in the end, not be interested in what's the temperature in any point on your notebook or on the screen, for instance. You may not be so interested what's the temperature in the screen. It's the part that you have on your lap that you're interested in. So you try to somehow adapt your model to do as little calculation as possible. And that's one of the tasks, to remove redundancies and reduce the complexity of the model so that you only compute what you need. and that to a certain accuracy. And that's the task of model reduction in a way. So this is just a very rough way of trying to define what it is. So here is a more mathematical based description. So we will always be concerned with the differential system of differential equations that describes the behavior of our states, like the temperature over time. T is time. We start at a certain value, x0, which in most cases we will set to 0 for simplicity. And then your dynamics is driven by a right-hand side function that has the usual assumptions that you know from the theory of ordinary differential equations for existence and uniqueness of solutions. We will not talk too much, or almost nothing. We'll almost not talk at all about nonlinear systems. We'll come to linear systems very soon. But I just wanted to give you a description, general description first. And then, and this is now the really important aspect, we do not consider this equation, which we call the state equation, alone. Yeah? As I told you, we may be interested in only part of the state information, or we may be interested in derived quantities from the states. So for instance, in a computational fluid dynamics experiment, you may not be interested in the velocity of the fluid in any point of your grid, but if you're designing a car, you may be interested in this CW value. That's just one scalar quantity. That's the aim of your computation, which describes how resistive is your car to the wind or to the, yeah. So, and this is described by the second equation. So you have a quantity of interest that you want to compute. And in most situations, oh, this is actually bad. For the most of the talk, I will use Q here. So, so it's the number of outputs we will call Q most of the time. I think for the first slides I used P, but then I switched to Q. So this number, call it P or Q, is usually much less than n. It can be 1 if you're only interested in a scalar quantity. Sometimes it's 5 or 10. And then the other aspect of this description is that you have input function u of t, with which you can control your system. You want to achieve a certain behavior, or you want to reach a target. Then you use your input function u to influence the dynamics of your system. And the number of quantities with which you can influence your systems is m, and this is also usually much less than n. That can be also just one value, develop over time, but it can be more. So in a way, what we have here is what is called a system in systems theoretical sense, with inputs and outputs, and this is a black box, printed here in blue. This black box is called sigma, and we are not so much interested in what happens inside. We just want to know if I influence my system with this function u, how does my quantity of interest behave? That's the important aspect. So you may have a very fine model here that gives you this behavior, or that gives you this mapping, but in many situations this very detailed model that we have inside this blue black box can be reduced in complexity. And this is why model reduction works in many situations, so that at the end you have basically the same output here for the same input, but the computations inside become much cheaper. All right, so here's this again. So the aim of model reduction, mathematically speaking, is to reduce the number of state variables which describe the dynamics of my system. And you want to do that in such a way that you still can drive the system with the same input function. So there's no change in the input function. You apply the same controls, the same quantities. And you want to do that in such a way that what you get out here as the output of the reduced order model is basically the same as for the original model. But you want to do it much faster. OK, so this is the aim of model reduction. So you should note here that in order to do that for a nonlinear system, you also have to do something to the functions f and g, because x is a vector of length n, and x hat is a vector of length r. So you cannot use the same f. You have to change the f as well. In nonlinear model reduction, that's an issue by itself, how to deal with this f. But as I said, in this course, we will mainly stick to linear systems. But there is nowadays a lot of work on nonlinear model reduction as well, and this is very hot research topic at this point. OK, so what we want to achieve now is we want to design this reduced order model such that our quantity of interest is approximated to a satisfactory tolerance. That's the aim. And that should hold for all admissible input signals, which usually are L2 functions. Sometimes you consider only piecewise linear functions or piecewise continuous functions. But in the mathematical setting that we do here, we will usually assume that u is a square integrable function over the whole real line. That in particular means that it's, of course, bounded. That's just a necessary condition. Sometimes you may want to reconstruct your states as well. There are many situations where you are interested in the full state, and this is covered here as well. Just we use here, instead of G, we use the identity mapping that, so the right-hand side here would just be x of t. So you could do that as well. But there are certain limitations in the model reduction methods that I will explain in that situation. Most of these, or the methods that I will discuss, always assume that the number of inputs and the number of outputs is smaller or much smaller than the number of states. So if you have the situation that you want to reconstruct the state, and you would want to know something really about the error, you have to use other methods. You can use our model reduction methods that we will discuss to do that. You can always reconstruct the state if you use a projection-based method, as I pointed out. But it's just, well, you cannot say anything theoretically about the quality of the approximation of the states. That's it. But often it works well, but you cannot say much about the quality. Another kind of problems, that's a slight generalization, and another a topic that we will also not have time to go deep into. Maybe at the end, if I have time, I will discuss a little bit of this, is if you have additional parameters in the system. And this is where the problem with the P and Q starts. Now I use P for parameters and Q for the number of output quantities. I'm afraid that that might be not consistent throughout the lecture. But having said that, I hope you can manage. And it should be clear from the context whether P denotes parameters or the number of outputs. So the parameters P are here assumed to be constants. They are not depending on time, and they can appear anywhere in your system. They can be, if you, for instance, have a parabolic PDE. I guess that Marlis talked about parabolic PDEs to some extent last week. Parameter could be the diffusion coefficient, or it could be the angle of the wind for your convection term in your parabolic PDE. That could be parameters. And these parameters could enter the system in such a way that the designer wants to do many test runs with your system and change these parameters. So he wants to see how does your system behave under parameter variations. And then you maybe have to simulate this system a couple of times. Not 2 times or 5 times, but 1,000 times or 1,000,000 times. Now, if you have 3 or 4 parameters and you want to have, say, they all live in an interval from a certain A to B, say, and you do a grid over that interval, then and you have 10 points in each direction for each parameter, and you want to test all combinations, you're already at 10,000 runs. Yeah? Even if you can solve the ODE in 5 minutes, if you have to do it 10,000 times, that's quite a computation. And this is where model reduction develops its strength, that if you have a reduced order model that can bring down the time for one simulation from 5 minutes to 5 seconds, that really pays off if you have to do 10,000 evaluations for different values of P. I also added here an E matrix to have a more general presentation. Think of a parabolic PDE, discretized by finite elements. You will have a mass matrix here. In all what I will talk about, E will be non-singular. You can do a lot of things if E becomes singular as well, and the model reduction methods have been developed for that case as well, but that is again too much material to be covered in one course. Okay, and if you have a parametric system, then of course your reduced order model must contain these parameters P as symbolic quantities in the reduced order model as well. Otherwise you haven't gained anything. If for a new parameter set you have to recompute a reduced order model, then it probably was faster to do the simulation of the original model and not go to a reduced order model. So your reduced order model, as I told you for the function u of t, which should be not changed in your reduced order model, also the parameters should not be touched in your reduced order model. They should be there as symbolic quantities. So as I said, we'll not get into too much into this area probably. I will decide that on Thursday, whether on Friday we have time to start in this area. Okay, now as I told you, we will mostly be concerned with linear systems, so that our right-hand side of the ODE is AX plus BU, A and B matrices, real matrices, E also real matrix, B is an n times n matrix because we have U inputs, and C is a P times n or Q times n. I'm sorry for this switching between P and Q. Matrix. So this is just to visualize this. A and E are square matrices, and in the general setting that we will see here, B will be a tall, narrow matrix with only a few columns, and C will be a small, fat matrix. And D is a small matrix, P times M. D is a small matrix of this dimension times this dimension. And often it is set to 0 anyway. It's not so often that you have a direct influence of the control on the input without going through the dynamics. But there are situations where you have that. And then if you go to the linear setting for the parametric system, you could have the parameter sitting in all these 5 matrices describing the system. But most likely they only sit in A. But there are situations where they sit in these other matrices as well. Okay, so this is now the setting. This is our dynamical system. So you could invert E because we have assumed that E is non-singular. And then write it as a standard linear ODE or system of ODEs. X dot equal, say, A tilde X plus B tilde U. I will not invert E as long as I don't need for reasons of numerical stability. Okay, now where did model reduction evolve from? So this is a little bit a historical perspective. And in the early 60s, when people started doing finite element calculations, they already observed that their computers were not fast enough to resolve the equations that they were developing in their finite element models. Here's just an example. It's a crankshaft of a Mercedes S-Class engine that we worked on in a project. And if you want to have a full model of the engine of your car, what you do is it's usually flexible body formulation or elastic body formulation, where you basically condense that finite element model of this crankshaft, which is very high, has a very high resolution of millions, with millions of degrees of freedom. You reduce it to something very small to fit into this framework of flexible body dynamics. And there, model reduction was developed first by means of what people in structural dynamics call modal analysis, modal truncation. And modal truncation we will discuss. It means that you only compute eigenmodes of your system. So that relates to Renn-Kang's course. You compute eigenvalues and eigenvectors. You decide which of the eigenvalues are dominant for your behavior of the system. Usually, if you have such a crankshaft, the system can usually not be excited by something in the gigahertz range. So if you have an eigenvalue with imaginary part of size 10 to the 6, say, or 10 to the 9, that will probably have no impact on the dynamics of your crankshaft at all. So you can throw it away. Usually you're only interested in this situation, in frequencies in the range between, say, 0 and 10,000 hertz. And then you only compute the eigenvalues of that model that are in that region. And you project your dynamics on the eigenspace corresponding to these eigenvalues. So this is modal truncation. You combine that usually with a technique that's called Guyane reduction or static condensation to get the stationary behavior of the system right. And that was developed also already in the early 60s. So this was historically probably the first wave of model reduction techniques. The second wave came in the 80s, or well, I could say it also started in the 60s, but it got a big boost in the 80s in control theory. So here we have a dynamical system. As I showed you, without the E matrix, just to make it easy, that's what's called in control theory the plant. Yeah? Now you want to design the U so that your model or your quantity of interest follows a given reference trajectory. So if you, say, want to fly to the moon, you want to get into the orbit of the moon. You don't want to miss it by a few thousand of kilometers, because then you go to outer space and you're lost. So you have to design your trajectory in such a way that you really get into the orbit. And you have to be able to compensate for perturbations. So if you launch your rocket on the ground, on Earth, you can pre-compute the trajectory that you want to fly, but you're never sure whether your rocket goes exactly up in the angle that is pre-computed. So you need a controller to be able to steer the system and to compensate for perturbations. Perturbations are modeled here by this W, which perturb the dynamics. And so what you do, you design a controller, and the controller takes your output signal, compares it to the reference signal, that's where you want to go, and then designs another dynamical system of which the output gives you the U. And cannot go into this here too much, or not at all, basically. this is the task of control design, designing a linear controller. The techniques, the modern techniques used are LQG design, H2 or H infinity control. The basic fact is that the dimension of that system down here that describes your controller is at least as large as the plant model. So if you have 100 differential equations here, you will have at least 100 down here. Now, what is a controller? Controllers are usually built as hardware devices on a DSP, it's called, I think. It's just a particular board, that a piece of hardware where the controller is hardwired. It's often not software, it's hardwired. And you can only hardwire a controller of dimension, say 10, nowadays maybe 20. So if you have 1,000 states here and your computed controller is of order 1,000, you cannot implement it in hardware. And that means you have to reduce either the size of your plant with model reduction, bringing it down to 10 or 20, and then design the controller, or you design the full controller and apply model reduction to that dynamical system. So there are two ways. The ideal way would be to go from the high order plant to the reduced order model. There are ways to do that, but again, we don't have time to talk that. But that was the motivation of model reduction in the area of control. And as I said, there was a boost in the 80s with the introduction of the method of balanced truncation, 1981 by Moore. And from there on, basically, all control design involved the step of model reduction. Or many control designs involved the step of model reduction. Okay, other application, and that was the third boost of model reduction, and it brought to light a new technology for model reduction that we will also discuss about. It's circuit simulation. So you all have computers, you all have CPUs in your computers, and the designer wants to know how the CPU behaves. And in particular, it shouldn't produce errors like you're probably too young to remember this Intel bug a couple of years ago, where a new Intel chip launched produced completely erroneous errors in some situations. So you have to do many test runs in the design phase of a microcontroller. And the problem is they get faster. And here you see what's called Moore's law up to 2011. That's what you find currently in Wikipedia. And Moore's law said that the number of on-chip transistors doubles each 24 months. Other people claimed it's all 18 months, but I think we are closer to 24. And this is basically true if you do a regression analysis of chip design since 1978. All right, and here is what happens. So if you look at this 1978 numbers, you had all the wiring on your chip, all the connections of your transistors, all this metal, the interconnect, was in one layer. And the distance between the wires was 10 micrometers. You had basically 2,300 transistors at a clock speed of 64 kilohertz. And that's what we had in 2007 in the quad-core technology of Intel. You had already 9 layers on top of each other, with a distance now only 45 nanometers, and you had more than 8 million transistors on the chip. So what's the problem with that, and why is this an issue? So the issue comes maybe if you look at this picture here. So this is a 3D plot of a chip, and that's a cut through. So here you have in orange, you have this wiring. Yeah, the transmission lines or the interconnect, how you want to call it. So suppose there's a signal passing through here. You all know that if you have a current along a wire, then this introduces an electromagnetic field. This electromagnetic field will be around this wire. And you probably also know that the amplitude decays quadratically with the distance, but because we are only 45 nanometers apart, maybe, this signal may have an influence on that wire. So if you have another signal passing by here, you have to be sure that the electromagnetic field introduced by this does not disturb this signal going down here, going along here. So this is so-called crosstalk. If the signal passing through here disturbs the signal here. So you have to avoid that, and in order to be sure that you can avoid it, you have to do numerical simulation. You have to come up with a model of this. And this will be a huge number of differential equations. Each of these transistors, just would it be one equation, you already have 8 millions. And then you have to add the network to this. And the transistor models are usually not only one equation, so it's really huge. And you cannot simulate that at all. Even with nowadays supercomputers, you could not do a full simulation of a microchip in a reasonable amount of time. So you have to identify large parts of the system of differential equations that you can describe by a reduced model. And this was driving model reduction in that area since the 1990s. And the methods that were used there come under different names. They first were called asymptotic waveform evaluation, Pde approximation, or they are implemented as Krylov subspace methods, usually with Arnoldi or Lanczos algorithms. And they can all be interpreted as rational interpolation methods, and we will explain how these connections come, or how these three different names for the same class of methods come together. Okay, there are many other areas that one could talk about. CFD, computational electromagnetics, chemical process engineering, design of micro and nano electrical mechanical systems, computational acoustics, you name it. Nowadays, model reduction is a technique that's used, as I said, almost everywhere in computational science and engineering. Just some examples to see what can be done. This is from the area of microelectronics. And here you use you have a professional tool called Simplora to have a thermic model of your CPU. So it's already in a simplified modeling, so the number of equations is only 270,000. And the model is so that you have 2 inputs and 2 outputs. And you're interested in the thermic behavior of a chip. So you let some signals go in and compute something, and you want to know how much heat dissipates. And that's a model for that. And if you then, there's one particular thing that is called the Bode plot that you want to, for which you want to compute the data. I will explain what a Bode plot is later on. And if you do that with the original model, it took 7.5 hours with the original system on dual core machine. And we could bring down the simulation time to less than a minute with reduced order models, depending on the accuracy you want, between 20 and 70. So we reduced the number of differential equations from 270,000 to 70, or maybe even to 20. That gives you a speed up factor of 18. If you include the time to compute the reduced order model, you never have to forget that you need some time to compute a reduced order model. So if that takes longer than the full simulation, you haven't gained anything. And if you exclude that problem, you have a factor of 450. And here you see, this is this Bode plot, which I will explain later on. And you see the Bode plot of the original system in black and the reduced order models in colored, and they are all on top of each other. So you get this information that you want, this Bode plot, to full accuracy in the eyeball norm. And here you see that the error, that's the relative error in that computation for this Pde plot. I will also explain that in more detail later, how to read this figure. For the model of order 20 is less than 1%, and for the model of order 70 it goes down to basically 10 to the minus 8. Yeah, so that's what you can achieve. Thermal problems are really good for model reduction, I have to say. Structural dynamic problems are more challenging. So this is a thermic problem, and we are really doing well here. This is just an example to show you that we can do nonlinear model reduction these days. That's actually a computation done by Tobias in his PhD thesis. It's a nonlinear system of partial differential equations. So you have a diffusive part here, and you have a sort of a reaction part here, which is nonlinear. It's a cubic nonlinearity. And this is coupled to a linear ODE. And this is a very simple model of a neuron in your brain. So depending on the input signal I0 here, which gives you the input, so to speak, into that system, that you can the information that you can get out of this model is whether your neuron will be firing and will build a new synapse or not. That's a very, very easy model for this situation. It's probably not used in neurosciences anymore, but it's a nonlinear PDE model, and we could, if you discretize it, it's only 1D PDE, so the number of degrees of freedom is only 800 here in this case. And we can bring it down to order 26. And this model develops limit cycles along the x-axis. So for each, if you go back, for each point on the x-axis, you will have in time a limit, the behavior, the dynamics of the system. And this is a phase diagram. Here's the x-axis, here's the v and v component, here's the w component. So in this phase diagram you have this limit cycle, which is one way that a stable dynamical system can behave. And you see in black the limit cycle is computed with the full model, and in red the limit cycle computed with the reduced order model. So we can do that with reduced order models as well. So that was just to show you that there is some successful work in nonlinear model reduction. Here now, last example, a model from combination of electrical and mechanical devices in the area of mechanical systems. This is a micro gyroscope. This is a tool that you will find in your car. And with that tool, I think Mercedes calls it ESP. It's a stability program in your car. If this tool can detect whether you're in danger of flipping over. So you may have heard of this ELK test many years ago, where Mercedes flipped when the Swedish journalists tested a new A-class Mercedes, and they call it in Sweden the ELK test, because you want to go along a road, and then there's an ELK passing, and you have to go around it. And in that test, the Mercedes flipped. So that led to the introduction of these devices in cars that can detect whether you're in danger of this. This is actually a model from Saab, a company that does no longer exist, I think. But it's not due to that, I hope. So the finite element model here is of order 17,000 basically, and because it's more or less a hyperbolic system, this discrete version, if you discretize in space, becomes a second order system of differential equations. Second order meaning you have second order derivatives. And that means if you go to the linearized version, you come up to basically 35,000 unknowns. And it has parameters. And the parameters in the design of the model are basically the width of this part, which is, if you make it too wide, this the device will be too stiff, and you will not be able to detect the tilting anymore. And then also the angular velocity here in these wings isn't a design parameter. You design it in such a way that you do not detect this tilting too early, but also not too late. That's the task in design. And then these parameters enter your model at various places. Width of the bearing is d, angular velocity. You also have two other parameters which come from the damping, which we did not consider here. This brings me actually to a point that my lecture will be accompanied by a research seminar given on Thursday by Heike Fassbender, where she will talk about model order reduction of second-order dynamical systems, meaning having second-order derivatives. I will not talk about that at all in the course, but she will build upon what I will talk about on first-order system, and will give you an introduction what special situation arises in second-order systems. So here you see now what was called a response surface. You vary the parameters d and phi along these two axes, and then you excite the system with varying frequencies. They run up here, and depending on that, you get a certain value for each d and for each theta, which you plot, and so you get a response surface, and due to the change of the frequency, this plot changes as well. And you see a movie produced with the original system and a movie produced with a reduced order model. I think in that situation we had a dimension of more than 200 for the reduced order model. It's not always that you can go down to 20, like in the thermic model. And you see that there's almost no difference. So for the design engineer, he wants to know how this response surface looks like. The one produced here from the reduced order model is good enough. So producing that movie probably took about a week. Producing that movie took a few minutes. So these are the kind of things that you can achieve with model reduction. Questions so far? Okay. Now I have motivated why model reduction is an interesting topic, hopefully. It's an important topic in computational science and engineering. Now we have to learn what are the basic ingredients. And so this part of the lecture will be a bit heavy, but we have to walk through this to really be able to follow for the rest of the week. The part on numerical linear algebra is probably a repetition for most of you. The other parts might be new for most of you. And this part of the lecture is you find in the second half of the lecture notes. We have this chapter on mathematical basics with a little bit more detail than what we will do here. So the first thing that is very important in model reduction, because it's already a model reduction method, if you think of it, it's a singular value decomposition. And I assume that you all know about the singular value decomposition. Therefore, I only want to show you how it can be used as a tool to reduce the dimension of a problem. And that's a problem that you took out of, or many of us that work in model reduction were inspired by the book of Jem Damel, Applied Numerical Linear Algebra. So if you read that book, you know the example. So what we assume, we have a digital image. We call it, we interpret it as a matrix X with nx rows and ny columns. And in each entry of the matrix, you have color-coded information, or the information on the color code for 1 pixel in your image, or grayscale information, whatever. So what you get is, if you store that matrix in your computer, say in single position, you need 4 times nx times ny bytes to store it. So now how can we use the singular value decomposition to reduce that? So this is the basic approximation property of the singular value decomposition, which also goes under the name of Schmidt-Mirsky theorem or Eckert-Young theorem. And it's probably, I hope, something you all know. The best approximation of rank R to our matrix X is composed of these outer products of the left and right singular vectors of X scaled by the dominant singular values. So this is, if X equals to U sigma V transpose is the singular value decomposition, then we take the first diagonal entries ordered by magnitude as usual, sigma 1 through sigma R, and the associated left singular vectors, which are the columns of U, and the right singular vectors, the columns of V. And then you can form this approximation to X hat, and it's known that the approximation error in the spectral norm, or the two-induced matrix norm, or operator norm, is the first of the neglected singular values. And we'll see that a very, very similar result will later on be derived for dynamical systems, where it's, of course, not per se clear what is the singular value of a differential equation. But we'll see that we can define something similar. So now the idea is, instead of storing the image X, we store the image X hat by only storing these singular vectors U1 through UR and the scaled right singular vectors, so you don't have to do extra storage for the singular values, sigma 1 through sigma R. And then you come down to storage requirement of 4 times R times nx plus ny. And if R is small enough, that gives you a reduction. And this is the image you find in Demel's book. That's a picture you can load in MATLAB. The clown, it's a very low resolution image, and it only requires 256 kilobyte of memory. And so if you go to a rank 50 approximation, you probably cannot see in that resolution any difference. And you go down to 104 kilobyte. And if you go down to rank 20 approximation, 42 kilobyte, you can still see it's a clown. So this is by no means a method of image compression. So if you work on image compression in your PhD thesis, for instance, you will work on more advanced and sophisticated methods with much better compression rates. But this is just an illustration what the SVD can do. In this area of image compression, as I said, there are better methods, but it's not so true in other areas where you can use SVD-based compression techniques. Here for a grayscale image, the reduction is often much better. So you have here 1.2 megabyte basically. And in that picture you see one of the heroes of numerical linear algebra, Wilkinson, Givens, Forsyth, Householder, and Ricci, and Bauer. Bauer, the only person alive. And here you see the approximation, so you can also go down to rank 50 without much loss of information in this picture. You probably will no longer be able to read the name tags, but that's difficult here anyway. So this is dimension reduction by singular value decomposition, and it works. Why does it work? Well, we have this approximation here using the largest singular values, and you have an approximation error which is given by, if you look here, by sigma 51 or sigma 21. And if you look at if you plot the singular values for the clown image and for this other image, you see that from the first one, which is of size 1, they drop very fast. And here is this rank 20 approximation, so you have an error of somewhere between 10 to the minus 1, 10 to the minus 2, and rank 50, it's basically 1%. And here you see also for rank 50, it's also again 1% basically for this other picture. So this is why it works. You have this Of course, they have to decay, unless, I mean, they could be constant, the singular values, but sigma 1 is the largest one always, and sigma n or sigma m is the smallest one. And usually they decay in some extent, but in these images, they descend very fast in the beginning. And this is why you can use the singular value decomposition as an approximation technique here. It's not decaying so fast that it's really a good approximation, as I told you, with JPEG that is based on the discrete cosine transformation. You get better compression rates. But it's not so true maybe in dynamical systems. We'll see that in dynamical systems, once we have defined something like these singular values for a dynamical system, that they often decay even much more faster than those singular values. Okay, and now we come, well, let me just go first to this manuscript. I have a little bit on, let me just switch to this for a second. You go to this, let's see. So you have this basic stuff that I just talked to about the singular value decomposition. There's a little more in this handout. So if you don't remember well, it might be worth in your free time to go through this page on properties of the singular value decomposition. And there's also some material on Krylov subspace methods that I don't assume I have to repeat because you did it in some way last week. So what I will now talk about is this introduction to systems and control theory. And let me just ask the first question. Who of you took a course in either one, system theory, control theory, or something similar? Okay, that's very few. So you can doze off for a while. So okay, let's go back to the lectures first. So the first tool that we need is the Laplace transform. It's one of the integral transforms that one learns usually in a math curriculum at some point, or sometimes you don't. I didn't learn it as a student. It's a sort of generalized Fourier transform. And if you have a function f, its Laplace transform is given by this integral expression. So it's an integral involving your function scaled by the exponential of minus st. So t is positive or non-negative real, so it runs on the real axis, and s is a complex variable. And this s is not in the it's not where it's integrated on, so it's the oh, this should be a capital F actually. Sorry, that should be a capital F. So this is a function now depending on that complex variable s. This integral, of course, you need to discuss whether it exists. I don't want to go into that. The necessary condition is that f is locally L1. That means it's Lebesgue integrable on each compact subset of the real line, of the real half line. We don't want to discuss this analytical background. So assume that for the functions to which we apply the Laplace transform, that integral always exists. One issue is with this mapping, we go from the so-called, this capital F here is now a function in the so-called frequency domain, or Laplace domain, and f of t was a function in time domain. So this is just notation. Okay, and in frequency domain, what we often do is a so-called frequency response analysis. And this was actually what I showed you in these pictures in the examples earlier on. You evaluate your function on the imaginary axis, on the upper half of the imaginary axis. That means you set in your Laplace variable s, you set the real part to 0 and you take off the imaginary part, or you consider imaginary parts that are non-negative. So this is the upper half of the imaginary axis of the complex plane. And if you do so, and then you do this evaluation, then omega, which I define here and further on we'll also call omega, the imaginary part of the Laplace variable, that can be interpreted as the frequency of your system. Yeah, so if you talk about the CPU at 3 gigahertz clock rate, the operating frequency will be 3 gigahertz. Omega in that setting will be in radians, so if you go to the frequency in hertz, you have to multiply by 2 pi. So there's a relation between these two measurement systems. Okay, so if I talk about frequency or frequency response analysis and so on, evaluation is always meant of the Laplace transform on the upper half of the imaginary axis. And the trivial consequence of this definition is that if you take the time derivative of the function f, then in the Laplace domain, this is just s times the Laplace transform of f. And this is important now. We will see in a minute why. Yeah, this you can, it's quite easy calculus to derive this. And this is why Laplace transforms are very popular among engineers. You can solve a linear ordinary differential equation by going to Laplace domain. It becomes an algebraic equation due to this fact. We'll see that in a second. And for ease of notation in the following, will do what I already did here unpurposely. Namely, I will not distinguish between, in the lettering between time domain and Laplace domain. It should always be clear from the context whether we will be in time domain or Laplace domain. So I will not use uppercase letters, because then I run out of letters too early. Okay, what can we do with the Laplace domain? We can now apply it to our dynamical system. Yeah, here it's again the linear dynamical system. Here it's what I recall, what we just learned. You map your function x of t to a function now depending on the complex variable s, and the time derivative is mapped to s times the Laplace transform of x. And that applied to our dynamical system yields this system. So it not much changes, just the argument in the output equations, and the time derivative becomes s times xs. And that now means you can now solve for y of s. Yeah? You just, let me just do that calculation here on the board to make it more obvious. So you put a to the left-hand side, so you get se minus a times x of s equal time bu of s. So this is what you get immediately from that equation. And now you solve. As long as s is not an eigenvalue of the matrix pencil A minus lambda E. And then you insert this expression here in the output equation, and then you get this. So what we now have is a map that depends on the frequency s from the inputs to the outputs. This is what I wanted to have earlier on. I told you we are interested in what happens if I insert an input signal u, what happens to the output. And here is a direct mapping from the inputs to the outputs. This function g of s is called the transfer function of our sigma, of our system sigma. And the goal now must be to have a fast evaluation of that transfer function. What kind of creatures are transfer functions? I just want to give you a very simple example here on the blackboard. Turning that off is. Can I stop it somewhere in between?
No.
No, just going up, okay. And this is all right. So what can happen with transfer functions? What kind of creatures are those? Just take a very simple example. E is the identity matrix, and A is -3, 1, -1, -5. So what is part of this transfer function? So let's just so this was our transfer function. I will specify B and C later on. So first of all, we have to evaluate this thing. So E is the identity. What we get is S plus 3, 1, -1, 1, S plus 5. So that we have to invert. Should be easy. What we get is okay. What we get is 1 over the determinant of this thing. That's the determinant. And then using a joint calculus, S plus 5, S plus 3, and flipping signs. So you multiply that out, and you'll see that this comes out nicely to be 1 over S plus 4. So you get this expression okay. So what we have here is a 2 by 2 matrix of which the entries are scalar rational functions, where the degree of the denominator polynomial is 2, which is the size of the matrix, and the degree of the enumerator polynomial is at most 1. And that holds in general for n. So the degree of the denominator polynomial is n, and the enumerator is n minus 1, or at most n minus 1. Okay, now we have to see what is the transfer function. So this is case 1, g of s. If case 1 is C equal to B is the identity matrix, and D is equal to 0. So that would be a case where we have controls in both of the differential equations in our system of differential equations in the linear system, and where we do full state observation. So y of x would be equal, y of s or y of t would be equal to x of t. Second case, so d equal to 0 we keep. We do b equal to 0, 1. In that case, we first compute this thing, SE minus A inverse B. And you see, okay, this just picks out the last row of this expression. So this is the last column of this expression, of course. 1 over s plus 4 squared and s plus 3 over s plus 4 squared. Now again, we can now see what the transfer function would be in the case A, where C would be again the identity matrix. In that case, the transfer function is now a column vector of two rational functions. Yeah? So depending on the structure of inputs and outputs, this G of S is a different creature. Now something interesting happens in the case B. Oh. Now this is not so interesting yet, but so in that case the transfer function becomes scalar because we now pick out only the last row. Okay, so this is really depending on the number of inputs and outputs. You have a matrix, a vector, a scalar. All of them are called transfer functions. And what you can read off from this transfer function is its poles, of course, in this expression. The poles are at -4. It's a double pole. And of course, these are the eigenvalues of A. And the transfer function also has zeros, 0 at -3. Just for those in control theory, negative zeros is good, negative poles is good. Positive zeros are evil, positive poles are even more evil. So usually if you want to design transfer functions, you design your model, you want to have stable models, so you want to have poles that are negative or in the left half plane, and you also want to have negative zeros, but that's another issue. So the third case that I just wanted to, I think I do it down here because it's very quick. Third case is D equal to 0, B equal to 0, 1 as above, and C equal to 1, 1. You could take 1/2 times 1, 1. That would mean that your output, your quantity of interest, is just the mean of the two state variables. In that case, if you do 1, 1, you get the following situation. So you add these two terms together. They have the same denominator anyway. So you see that in that case you have a pole zero cancellation. And that means, first of all, you only have a single pole now left instead of two. You don't have any zeros anymore. And you can realize the same dynamical system, the same transfer function, with the following setting. You take C equal to 1. So now this is a dynamical system with only one differential equation left. Yeah? The differential equation is x dot equal plus 4 minus 4x plus u, and y is x. So we have the same behavior, the same mapping from input to output for this dynamical system as we had for this 2×2 case. And this is because of this pole zero cancellation. That means our representation of the dynamical system that I had here was not minimal. I could, without losing any information, I could reduce an equation. I could throw away an equation. And this is due to the structure of the input-output relation. Yeah? So we have only this left. Okay, so this is transfer functions are matrices of which the entries are rational functions, where the denominator polynomial has degree at n in the generic situation, and at most the denominator polynomial has degree, the enumerator polynomial has degree at most n minus 1. But in the case of pole zero cancellations, the degree can be reduced, and that means that we do not need all of the differential equations that we had used in our model. And this is quite a natural situation if you use if you're an engineer and use automatic modeling tools like Modelica and something like that, that you get redundant equations in your system. This is an important information or important observation that we will also come back to in the exercises. Yeah.
So if we work with a transfer function, then we automatically like missing the secondary goal of tracking the states.
In a way, yes. That's what I meant. We always have this point of view. U and Y are the important quantities. As I mentioned, later on we will see that from the model reduction methods we use, even if they are based on you working with the transfer function, you will be able to reproduce an approximation to this state. It's not clear how good that approximation is. We will get an error bound in the output quantity, but will not get a useful error bound in the state. Still, the state approximation might be useful. Good. Now we can formulate the model reduction in frequency domain using this this calculus. So we have our dynamical system, we have the reduced order system here. And for both of them we can derive this expression. Here for the original system, and you can do the same for the reduced order model. And then what you get is that y minus y hat you can write as g times u. Well, maybe use, for now we use arguments. So this is what you get now in the frequency domain from the difference of these two systems. And then, because, as I said, we have the same u, now taking norms for this equation, you end up down here. And then this whole problem turns out to be an approximation problem for the transfer function. So a rational approximation problem. You want to approximate this matrix valued function g with another matrix value function g hat, of which the denominator polynomial has a much lower degree, namely r at most, than the original transfer function. So this is a key observation for all the model reduction techniques that we will discuss, that in frequency domain, after applying Laplace transform to our systems, we end up with an approximation problem for the transfer functions. So we are completely going away from the functions x of t or x of s, u of t, u of s, y of t, y of s. We are left with the problem of approximating g by g hat. Okay, now details or some concepts in control theory. This you cannot find in the slides because I only put it into the slides last night, but you'll find it in the in this handout is at the end of the thing, the chapter 1 or chapter 2 in my notation. We have to say what is a stable system because we will mostly be concerned with stable systems. So stable system means that all the poles of the transfer function are in the left half plane. As I just mentioned, this is usually nice. In our small example here, this was the case. Both poles were -4, so they are in the left half plane, so that's a stable system. And stable in its original meaning means only that they could be on the imaginary axis if they are simple. But we will usually not consider systems which have poles on the imaginary axis. Because then this expression would not be well defined on the imaginary axis, and that's where we are usually evaluating. So we assume that we don't have poles on the imaginary axis, so we assume that the system is usually asymptotically stable. That means all the poles are strictly in the open left half plane. And this also goes under the name of Lyapunov stable or exponentially stable. And for nonlinear systems, these are 3 different concepts. But for linear systems, they are all the same. And sufficient for this is, of course, that the matrix A has all its eigenvalues in the left half plane. As in our case here, the eigenvalues were -4. They turned out to be the poles in the 2 first cases. And in the third case, one of the eigenvalues was the pole of the transfer function after the pole 0 cancellation. So it could be that A has a eigenvalue in the open right half plane, and the system could still be stable because you have a pole 0 cancellation with a 0 that's also in the right half plane. So if you have a pole at 5 in your system, or if you have an eigenvalue at 5, but in the transfer function description you have a 0 which is also at 5, these two cancel, and you still have a stable system if all the other poles are in the left half plane. Yeah? So this is only sufficient, yeah? But not necessary. A could be unstable, could have eigenvalues in the right half plane, but due to possible pole 0 cancellation, the system could still become stable. One thing that is often a little bit confusing in system theory, that we talk of stable systems if we mean asymptotically stable systems. Because, as I said, we usually assume that we do not have any poles on the imaginary axis. So in that case, if you have a stable system without poles on the imaginary axis, it's asymptotically stable. And therefore, one often skips the asymptotic or asymptotically and just talks about stable systems. So, and now comes the tricky part. We have to go through this rather quickly because I don't want to waste my time on this, but rather work on model reduction. So stability is one of the properties of a dynamical system, but there are other properties that play an important role, and particularly controllability and observability play a role, and I will do that. I actually plan to do some of that on the blackboard, but because of time, I think I'll just guide you through my lectures, through my notes here. We'll make that larger. So this is definition of controllability. I will show you a picture which makes it more clear. So you have your dynamical system. I think I skipped here the E matrix. We assume here in this chapter E equal to the identity. It's not a loss of generality because, as I said, you can invert E and then introduce new matrices A tilde, B tilde, C, and so on. And you have x dot equal ax plus bu. And this concept of controllability only is related to these two matrices A and B. So the output equation doesn't play a role for this concept. What's important is you have initial state, initial condition. So here's your x0 somewhere. And now you ask the question, can I find a function u, an admissible function, in our case an L2 function, so that after a certain time x0, I come here? Can I reach x1 from x0? And you can pose different questions. You can say, okay, we have a fixed time, capital T, for instance, or T1, I think I called it, and I want to reach my target in time T1. Can I find a U that does this? Or does there exist a T1 such that I can reach my target? And these are different questions if you have a general nonlinear system. In the linear case, all these three definitions that I wrote down there collapse. They coincide. They're all the same. If I can reach x1 in time t1, I can also reach it in time t2. In any time t2 greater than 0. Yeah? And this is just one of the standard properties of linear system, or of linear ordinary differential equations, basically. You can always shift the time or replace the time by a new time, which is a scale time, and nothing changes in your ODE. This is not true in the nonlinear system in general, or nonlinear differential equation. Okay, so this is the concept of reachability. The related concept is, given a target x1, yeah, you have given now a target x1, which are the initial states that I can reach, from which I can reach x1. Yeah, so I've given the target, and the question is, which are the initial states for which I have a u so that I can reach x1? And again, for linear systems in this form, these two concepts are the same. For nonlinear systems, they are in general different. So we talk about reachability and controllability sometimes, and both are the same concepts for linear systems, but make a mark in your brain. For nonlinear systems, these are different. Question? Yeah? By linear, you mean linear time invariant? Linear time invariant A is always a constant matrix. And time varying cases, some of the linear concepts are the same, but some are different here, but I don't want to go into that. So A and B are always constant matrices here. Good. Now I can, this letter question, I can now pose in the following way. So given the target x1, which are the states x0 so that an admissible control exists that with that control I can reach x1 at time t1. So this is the set C of t1, the controllability set. And if this set is the whole of Rn, then we say that the system is completely controllable. Now it's clear if I can reach the target from any initial state anywhere in Rn, I'm very well off. Okay, so what else? So important concept that you know from your Calculus 1 course or whatever, Differential Equations 1 course, is to analyze the situation, whether it's possible to reach from to go from x0 to x1 is the analytical solution of a linear constant coefficient ODE, which is given by the variation of constants formula. And for that, inhomogeneity, the variation of constants formula gives you this expression over here. Yeah. And if you insert that in the output equation, you get that expression for the output. And we don't want to prove anything like that. That's basic theory of ordinary differential equations. And you know that, and this holds even in much more general situations. If you have this operator E of t minus s here, this is the fundamental solution of your ODE. This fundamental solution has the so-called semigroup property. That's if you go from S to T, it's the same as going from S to T hat, and then going from T hat to T. Okay, and this is, of course, in our situation, the fundamental solution is just this exponential map. You have seen in Marlies Hochbuch's talk and also in Nikayem's talk last week, probably. And this has, of course, this property. Even without knowing anything about the theory of ordinary differential equations, this property can be proved algebraically. Now the question is when, or the question that we have to pose, or we already posed it, can I get from x0 to x1? That means I have to find a u that if I insert it in that equation, so the question is, exists u such that x of t1 is equal to, now we use this equation E of at1, x0, no, x1, x of t1, x0 plus 0 times t1 minus as. So is there such a u? And it is easy for a linear system. We just make the ansatz u of t equal b transpose e to the minus a transpose tc. Why is that a good approach? We will see on the next page. C is a constant that we yet have to choose. Because you now get, this is the formula I had here, down here. And I just to remind you, we make the ansatz u of t is equal to b transpose Gesundheit transpose t times c. Okay. Okay, and then you see you can, if you insert this, you can write this equation in this form. We bring this exponential of a times t1 to the left-hand side. The exponential matrix is always invertible, as you have learned last week. So we can solve this, bring x0 to the left-hand side. And then we are left with this expression. And the c is a constant. We can pull that out of the integral. And we call this thing here, this integral from 0 to t1, with the two exponential functions and bb transpose in the middle, we call that the Gramian of the linear system, finite time Gramian. This is what you have here. So now the question whether we have such a function u that brings me from x0 to x1 boils down to the question whether there is a unique constant c for solving that equation. So c is the unknown so far. Everything else is known. And can I solve this equation for c? And of course I can do that if P is invertible. Now, if P is an invertible matrix, then I can solve for c. I can plug in my c, and I know that I have found a control function u that brings me from x0 to x1. And that is then the definition, or that is, well, a characterization of controllability. So x0 is controllable to x1 if this finite time Gramian is non-singular. And of course, if you look at it, BB transpose, it's a symmetric matrix, non-singular symmetric matrix, and it's positive semi-definite anyway, because the BB transpose is positive semi-definite. It's a positive semi-definite matrix no matter what A and B are, and if it's non-singular, it must be positive definite. And there's actually a typo still in your lecture notes. Everything that's yellow here must say definite, not semi-definite. Okay, so that's one issue. And then you know this integrand here is a continuous function. And if it's positive definite for 1t, then it's, if you extend t to infinity and do a substitution, before you can run this to infinity, you actually have to consider the inverse of p of 0 of t1, because if A, as we assume, usually is stable, then in general, if you let t1 go to infinity, this integral will go to infinity as well, because you will have exponentially growing functions here. If you want to go to infinity, you look at basically the inverse of this that you obtain by a variable substitution, and you end up then in the limit for, after the variable substitution, s equal to minus t, you end up with this integral. It's an uneigentliches Integral heißt, improper integral. But it's well defined if A is stable, it's a stable matrix, because then that's an exponential decaying function and the integral converges. This is a positive semi-definite, and again, if that was positive definite for 1t, that thing is positive definite as well. And that means that we can characterize controllability of a linear system by the Gramian, this is an infinite time Gramian P, which is this matrix down here. And then, having said this, there is another way to characterize controllability by the so-called controllability matrix. It's K of AB. And that looks pretty much like a Krylov matrix. And it's a Krylov matrix, block Krylov matrix, where you run all the way up to n. And there's an intimate relation of that matrix to this expression that I cannot go into too much detail, but the following theorem is important. For linear time invariant system, meaning that A and B are constant matrices, this controllability set at T1, the set of all initial states that can be controlled to x1, is the range of the controllability matrix. And that is proved using this relation of the Gramian to the controllability of the system that we have just worked out. And now you look at the right-hand side here, that doesn't depend on T1 anymore. So that means C of T is a constant set. It doesn't change in time. And this is the consequence that I wrote down here in the second theorem. C of T1 is equal to C of T2. So C of T is independent of the time, and we can also show that C of T is independent of the target, because the target, x1, also doesn't play a role in this right-hand side. So no matter what x1 is, no matter what T1 is, the controllability set is always the range of the controllability matrix. And that means that for controllable systems, this controllability system set is just Rn for all targets in the Rn. Okay. And yeah, this I already have said here. That's what we showed up here. If P is this infinite time Gramian is positive definite for one T1, it's positive definite for all T, and so on. And then this is still not so easy. This is an improper integral of a matrix-valued integrand. We will learn how to compute it, because this is actually can be solved, or this P can be computed by solving a matrix equation, which is the second part of this course. You don't have to solve the integral, but it's still quite a computation. Computing this is also not really feasible if n is large. In particular, determining the rank of this is not easy in finite precision arithmetics. So there are other tests, other characterizations that I summarized here in the so-called Hautus-Popov lemma. So it's equivalent that the system is controllable. The rank of the controllability matrix is n, so it has full rank. If you have a left eigenvector of A, then that cannot be in the co-kernel of B. It cannot be in the null space of B transpose. Yeah, that is true for any eigenvector of A. So you have, if you want to do that test, you would have to compute all the eigenvectors of A, or all the left eigenvectors of A, and test this condition. And oops, there is another. You can write this last condition also in this way, that the rank of this augmented matrix lambda identity minus A comma B is n for all lambda in C. Now that's the same, well, it's part of the proof, that's the same as the previous condition, but that's very easy to see. So this is an n times n plus m matrix, so it's a rectangular matrix, and for any lambda in C it has to have full rank. And then the last but not least condition is that the controllability gradient P, this integral that I just showed you, is positive definite. So this is the important characterization. And then there are some examples that you may want to work through if you want to familiarize with this concept. And there is a brauchen wir Observability auch noch? Yeah, minimal. Just for the last 5 minutes, the question is whether a system is observable, whether the output y of t gives you sufficient information to work with it. That's very loosely speaking. Yeah, you know, we have already discussed this. We don't have the full state information possibly at hand to design a controller or whatever do with the system. We only have our quantity of interest y maybe. In a practical situation, that may reflect the fact that you only be able to measure part of the state. So is this what we measure about the state, this y of t, is this sufficient to design a controller? And this is the concept of reconstructability or observability. And that means, suppose we have two output functions, y of t and y tilde of t, which we have measured, and we have measured them to be the same. Can we conclude that they belong to the same system? And this is the question of reconstructability. I will not go into the details here. That's important for control theory. But just the characterizations are the same as we have them in the case of reachability or controllability. And system is reconstructability if and only if the dual system, these minuses are missing in the slides, and there's still a plus too much here. If that dual system is controllable, the system is observable if and only if this matrix, which is called the observability gradient or the infinite observability gradient, which looks pretty much like the one we had in the controllability case, just the transposes are at the other positions, and then we have C transpose C here instead of B transpose, if that is positive definite. And of course, due to this duality argument, we have the same Haughton's Popov test. And we can also define an observability matrix, which is sort of a transposed controllability matrix of A, C. Yeah, if you transpose A, transpose C, take the controllability matrix, then this is the transpose of the observability matrix, and you have the same testing now with the right eigenvectors of A. So if a system is observable and you have a right eigenvector of A, then this right eigenvector cannot be in the null space of C transpose. Or you have a full rank property of this now n plus q times n matrix. So these are very similar concepts. And the last but not least thing I wanted to mention here a system that is both controllable and observable is minimal. Minimal means you don't have pole zero cancellations. Yeah, so we had this pole zero cancellation in that example. If I put this special C matrix in there, and that means that system was either not controllable or not observable. Or maybe it wasn't neither controllable or neither nor observable. So that could be the case. But in the other two cases where we didn't have the pole zero cancellation, that reflects the fact that in this example 1 and example 2 settings, the system was both controllable and observable and therefore minimal. Okay, and then there are also, you can weaken these concepts of controllability and observability to what is called stabilizability and detectability. We will not make use of these concepts too much in the course. You can have a look at them in your free time. They are a little weaker than observability and controllability, but as I said, controllability and observability are really concepts that we will make use of the whole week. In particular, the relation to these gradients and the fact that controllable plus observable means minimal, means no pole zero cancellation. So that's all for today.